This chapter is a chapter on stereochemistry. What we're covering in this chapter are chiral carbons. And chiral carbons are those that give rise to what we call stereoisomers. We've already looked at stereoisomers with cis-trans stereoisomers. Now we're going to look at another type of stereoisomer. A chiral carbon or a chiral molecule means it's handed, as in right hand or left hand. Just as your right hand does not fit inside a left-handed glove and a left hand does not fit inside a right-handed glove, you would have molecules that were chiral not fit inside their mirror images. If you hold up your hands in front of your face, you will see that one hand is a mirror image of the other, meaning that the left side of your right hand looks just the same as the right side of your left hand. But you can't take your right hand and insert it into your left hand and have things look right, because then the back of your hand would be where the front of your hand is supposed to be, etc. So a right hand and a left hand are what we call non-superimposable mirror images. And that's what we're going to talk about here in this chapter. We're talking about carbons which have a mirror image that are not non-superimposable. This comes up when you have a tetrahedral atom, so that means it's going to have 4 groups on it, and each of those groups are different. Now, carbon can have 4 bonds on it, so it easily can have 4 different groups on it. There are other atoms which can be chiral and have non-superimposable mirror images, but right now we're going to focus on carbon. Here's a picture of what we're seeing with a carbon, the black atom here, and 4 different groups. So we have 4 different color groups on here. Now if you would get your model set and create a carbon with 4 different color atoms attached to it, you're going to be able to look at what we're doing and see it better in 3 dimensions in these images. So make actually 2 chiral carbons, make them so that they have 4 different groups on each, and you will find if you do it correctly, you can make them mirror images of each other that are non-superimposable. When you have 4 different groups on one atom, you have the potential for non-superimposable mirror images, and we call the carbon with 4 different groups on it a chiral carbon, or we can call that atom a chiral center. Let me just show you with this image how this and this, although they look identical because they have 4 of the same different groups on them, they are non-superimposable. So I'm going to lift this one up, turn around, and bring it closer, and you can see here the yellow and the yellow line up, and the pink line up, but the blue and the red are switched. They are not the same. They are non-superimposable because the blue and the red are switched. Okay, so now it says green and red. This one is supposed to be green, but PowerPoint changed the color. All right. Enantiomers are non-superimposable mirror images. So we would say that this and this pair are enantiomers because they are non-superimposable mirror images. So when you have a carbon that is chiral, 4 different groups on it, you can have enantiomers. All right, so again, this is stating an atom is chiral if it's tetrahedral and has 4 different groups attached, and you get 2 non-superimposable structures, which we call enantiomers. What you do is you look at each group attached to see if there are 4 different groups. If there are 4 different groups, then the atom is considered to be chiral. Let's talk about what a group is. A group is not the immediate atom A group is the immediate atom and everything attached. And this is sometimes you have to, you don't get this right away until you go through a few problems. We often will put a star next to the atom to indicate that it's chiral. Not always, but we can. So now what I want you to do is try to identify in each of these molecules what atom, if any, is chiral. What I want you to do is start with this first molecule and try to find a chiral carbon in it. Pause, try to figure it out, and then restart, and then we'll do the next molecule. Okay, if we look, we can see this carbon is not chiral. Why? Because there are 3 hydrogens on it. 3 hydrogens get you have more than, well, you have 2 groups that are the same, so it's not going to be chiral. If I look at this carbon, you can see this group and this group are different, but you have 2 hydrogens that are the same, so this carbon is not chiral. And if I look at this carbon, there's 3 hydrogens on it, so it's not chiral. If I look at this carbon, I will see that this group is an ethyl, this group is a methyl, then there's a hydrogen and a bromine. So there are 4 different groups, so that carbon is chiral. Now go to this molecule and try to identify which carbon is chiral and see if you can determine if there are any chiral carbons. If so, which one? Okay, if I look at this molecule, you will see we can exclude this carbon and this carbon because they each have 3 hydrogens on it. We can exclude this one and this one because each of those have two hydrogens on it. If I go to this carbon and this carbon, I can exclude both of those because they have a double bond. They are not tetrahedral, they're trigonal planar. You must have sp3 electron geometry for there to be chirality. If I look at this carbon, initially you might think, oh, 4 different groups, so I'm going to have a chiral carbon. And this group is one group, and this is one group. But if I look, this is an ethyl, and this is an ethyl. Those 2 are the same, so this carbon is not chiral. This entire molecule we say is not chiral because there is not one atom in there that is chiral, nor is a molecule asymmetrical enough on its own to be considered chiral. This one's chiral because this carbon is chiral. This one's not chiral because there are no chiral carbons. Now go ahead and look at this molecule and see if there are any chiral carbons in this one. Remember, you don't have the carbons and the hydrogens written out, so you have to think about the hydrogens being on the carbons and what each point represents on these structures, okay? All right, so now what we're going to do is look at each of the carbons in this molecule to see if any of them can be chiral. If I look at this carbon, there are going to be 2 hydrogens attached, so automatically I can exclude that. If I look at this carbon, there are 2 hydrogens attached, so I can exclude it. I can exclude this one because of the double bond. It's not tetrahedral. I can exclude this one because of the double bond. It's not tetrahedral. Now if I look at this carbon, it is tetrahedral, and what's attached? There is a hydrogen that's not written, a chlorine, then there is CH2, CH2, and this, and over here there's a double bond. So this group over here is different from this group. So if I look at how many groups are on it, there's a chlorine, a hydrogen, this side, and this side, so there are 4 different groups on it. And so now we can say that carbon is chiral, and the entire molecule is chiral. Now try this molecule and see if you can figure out this molecule. All right, let's go through, and immediately I can eliminate this because 2 hydrogens are attached. I can eliminate this one because 2 hydrogens are attached. I can eliminate this one because 2 hydrogens are attached. And this one I can eliminate because they're both in a double bond and they're not tetrahedral. This carbon has 3 hydrogens attached, so I know it cannot be chiral. If I look at this carbon, there is a hydrogen attached, there's a methyl group attached, there's this side that is different from this side. So there are 1, the hydrogen, 2, 3, 4 different groups. This carbon is chiral